Good morning to everybody, or good afternoon, or good evening, depending where you are. We are starting now the FRINGE session devoted to data products and services. Let me remind you that you can write your question in the Slido panel. You should choose the chart relative to this session, data products and services, and you should write the name of the presenter to whom the question is directed to. So let's start the session. The first presenter is Luis Bessi from Skywatch. So please, Luis, share your screen and start the presentation.
Okay, thank you. All right. So I'm presenting the developments in SNAP in the Sentinel One Toolbox. So SNAP is a multi-mission scientific toolbox. It's been around since 2014.
Sorry, Luis, we see your what do you call it, the presentation mode, and you should switch screens in the display settings. Yeah, that's perfect. Thanks.
Okay. Is that the right screen now?
Yes.
Yeah. Okay. All right. Just the current team right now is Skywatch, Sensar, Brockman, CS France, CS Romania, and of course ESA. SNAP is open source. It's made up of several different toolboxes from different projects, different sensors. We've got Sentinel One Toolbox concentrating on SAR, and then other toolboxes for other sensors and missions. And we've had quite a bit of growth lately, and it's been steady throughout. So since 2015, we've had about 30,000 or so unique downloads now for version 8. Version 9 is coming out in the summer. The cumulative downloads, a lot of Windows 64 users, and a growing number of Linux users now. And since 2015, we've basically touched every part of the world, has visited the website, downloaded the software, yeah. So for the Sentinel One Toolbox, we have quite a bit of SAR functionality that's been growing into the toolbox. Everything from calibration, speckle filtering, terrain correction, interferometry, telemetry, soil moisture, etc. And the supported missions is ever growing. Recently, we've added ISI, Capella, Salcom. And one of the main things that the toolbox provides is a common product model that takes any of those missions, abstracts the data, puts it into a common format, and then have all the processors and analysis tools work on just that common format in a standard way. So this is some of the new data sets. Capella at 50 centimeter, ISI, X-band, and Galfan 3 has been added. This is one of our pull requests that we've had recently from KSAT. And a new space player is Spacity. So this is the 1 meter spotlight data that they're providing. So some of the new features that have been recently added, the Copernicus 30 meter and 90 meter DEM, so automatic downloading, tile selection and resampling. And the Sentinel One orbit files, this is now operating from the GNS hub. We've also added the multi-temporal RTC composites. So this takes the terrain flattening, and you could put in a mosaic of ascending, descending passes, put them together, and have them seamlessly create a composite. So you can see here the shadow in the composite gets removed. We've also added Faraday rotation to assist in some of the low frequency sensors. And soil moisture application from Agriculture Canada. Some of the new developments in the support and education. So we're consistently adding new tutorials. There's recently been land cover classification tutorials, telemetry, updates to the SAR basics and INSAR, and the multi-temporal displacement mapping. So this one here just showing the temporal decorrelation. And then other INSAR related updates, we have the multi-master INSAR tool, which lets you select the pairing from the baselines and top put. And we've also added tools for the Spotlight co-registration. So this adds in the demodulate and remodulate in the co-registration. And this removes some of the artifacts from the interferogram. So coming up, we have Snap 9 to be released sometime this summer. We're going to have a new default file format from ZAR, and this is going to replace the Beam DIMAP. We're also going to be supporting the Cosmos SkyMed Next Generation, updates to the DEMS, automatic downloads for Aster. We have a product group feature, which is something that has been waiting for a while, which is incremental processing of the stacks, and updates to the Sentinel One product itself. Okay, and yeah, so that's it. So visit the website for any tutorials or downloads, and also the user forum. Thank you.
Yeah. Thanks a lot, Luis, and good morning, good afternoon, everybody. It's now my turn to introduce Alexander Jacob from EURAC Research that will provide a presentation about the concept of the SAR Cube project.
Thank you for the introduction. I would need the share screen option. Okay, now you should be able to see my screen. Whoops. So hello everyone, happy to be here to represent the SAR2Cube project. SAR2Cube project is a ESA project funded through the Open Call and the EOEP5 program. And in this project, we try to develop a new concept for how to organize SAR data to be more efficient with storage when we do applications based on the SAR data then later on. This project, we do it together with Descartes Technologies from Spain. You can also see here all the people who are involved in the project, and you can contact myself for any kind of questions later or during this talk then also. I will give you a quick overview of where we come from, what the project is all about, a little bit about the data cube concept, and what we define as our ARD-based data for doing the SAR processing, the processing environment, Openyo, tool that we use to make to access the data, the specific operators for SAR processing that we've implemented, some performance calculation and application examples that we implemented, then also to demonstrate that this actually works. Generally, we started from another project in 2017-18. We started with the Asia SyncoMap project. In this project, we did land cover mapping based on interferometric coherence amplitudes. And during this project, we generated quite a lot of data. This project, in fact, was so big that we generated 111 terabytes of data just analyzing 3 different study areas in Europe. This gave us some idea that we have a problem with respect to storage and SLC data, so that we need to find more efficient ways of dealing with the data when doing analysis. There is also another presentation about some outcome of this project tomorrow in the land cover and vegetation session, if you're interested, by my colleagues from University of Alicante. Generally, how do we tackle this problem is all the big data. We try to implement a new processing chain to do this and be more efficient with our storage. In the initial project, we pre-processed all the data so that every product's interferogram coherence and so on were pre-computed. Now we try to do this on the fly in SAR2Cube. So we have all of our nice data available through the Copernicus program and the Sci-Hub and so on. And what we want to do are all the nice applications, persistent scatters, land cover mapping, or change detection based on SAR time series. And how do we get there? Of course, we need to access the data. For this, we can use the standard interfaces. So the Sci-Hub, for example, downloading the orbits, the elevation model, and so on. And then we do pre-processing in order to generate something which is we call it level 0 data, or our analysis ready data, base data, let's say, that we need to do the processing that we put into a data cube. In our case, we use the open data cube here. There we try to put all the important layers and auxiliary information that is needed to do all further processing. And then based on this, we generated on-the-fly operators to generate the different SAR products, like the backscatter intensity amplitude images, or the coherence, or interferograms, basically. And finally, on top of this, we implemented all of this using Openyo. So this is accessible in a standardized way and also through various programming interfaces and different programming languages, so that can reach as many people as possible to then do final implementation of our use cases. So what is the base data that we have? Okay, first of all, we have our SLC data that we download, and then what we need to do is we need to co-register the data within one stack coming from the same relative orbit. That's the image alignment phase. We do some radiometric calibration to sigma, for example. Then if we deal with Sentinel One data, of course, we need to take care about defogging and debursting. And of course, we have also multiple polarizations available then here. But for INSAR, we need more. If you want to work with the interferometry, especially the differential interferograms, then we need also the topographic phase component. So that's another layer that we add to the data cube that we pre-process to be efficient here and have it available. And then finally, to also easily switch from the slant range geometry to a projected coordinate system, we also provide pre-processed, let's say, lookup tables for the coordinate transformation between the SLC data and some geographic coordinate systems of choice. We prepare this usually at least in the lat long WGS84 and then also in UTM based on the Sentinel-2 grid, so that we have these two standards available to make it easy to link to, for example, Sentinel-2 data. Then we put all of this data into a data cube, in our case, the open data cube. So we need to do the indexing of the data. And here we can already see how this then looks from the data cube perspective. So we have our complex components of the two polarizations, the real and the imaginary part. We have the grid for transitioning between the two coordinate systems, the SLC slant range geometry, and then, for example, the lat long grid. And then we have the topographical phase component. We can also add additional things like the local incidence angles and the DEM that has been used during processing, so that this can be available later. In our case, by preparing this for the whole range of available data until the end of last year, 2020, we generated around 1 terabyte of data per year. Then this is already much less than what we did when we had all the pre-processing done in the Syncomap project, for example, where for just 1 year of data with all the different pre-processing steps that we needed to do, we had already 17 terabytes for comparable. So there's around, let's say 15 times less data from the data provider perspective that we need to organize here. Then all of this we put into our Openyo infrastructure that we have already running at UREC. So we have here the data pre-processing phase, where we actually also used the Sentinel toolbox, which we have just heard about in the previous talk. So that we use to generate all the information that we put then into the data cube. The data cube is running in a dedicated virtual machine, which is also linked to a Dask cluster. And then this is accessible through the users, through our Openyo interface, through different programming languages. What is Openyo? Openyo has been a Horizon 2020 project, which has been run for 3 years. It's just finished last year. In this project, a standardized API for processing has been defined to render it independent of what kind of data structure you have in your backend or cloud computing facility with respect to the clients that are using this. You can find more information about this on the website openyo.org, or also in this paper that has been recently published in Remote Sensing by my colleague Matthias Schramm from the University of Vienna, who are also the lead partners of this project. Where we have Openyo, then we can directly link also what we do in our workflows to the existing software ecosystem in Openyo, which means that there are a lot of client software and tools already available. In this example, for example, the web editor, which has been developed by the University of Münster and Matthias Mohr there, and we can just reuse these tools so that the software stack that we have developed here can be available easily to many people in different contexts. Coming to the details then here. So we have the different operators that we can work on now from the data cube. Of course, this classic data cube operators that everyone knows. So you can subset your data, be it temporally or spatially, by having our lookup tables. Also the requests people can do, the data area extends just by defining an area in any coordinate system and then get the corresponding slant range geometry subset of this, and then we can do processing, multi-looking, and then also the geocoding. These are the standard operators, let's say, and then we have, of course, also the more SAR specific operators, be it working with the intensity or amplitude, as you can see defined here, which just gives us basically the signal strength over an area. This can be expressed in this formula using, for example, the web editor. In Openyo, all the processing is graph-based, though. So what will happen is that whatever you provide as a formula will be translated into a graph. This graph represents just this mathematical formula. Another nice advantage of Openyo is that all the processing is fully chainable. So this graph can be just put into a much bigger graph, which defines the access to your data sets, all kinds of other operations, for example, geocoding part that I mentioned earlier, and finally the storing of your result in a data format of your choice. The calculation of the intensity is then just an operator in this larger chain and can be run there. And finally, when executing this, you get your rendered image of the intensity that is being computed or the amplitude, as you can see here. Then other operators, of course, that we work with are for the coherence. Even this can be expressed as an Openyo graph. And since everything is calculated on the fly, we can also easily change, for example, the kind of multi-looking that we apply. We maybe for depending on the type of analysis we want to change it. This you can see here, the multi-look is defined in this graph, 3 by 15 or 4 by 19, as you can see here. And then you can easily calculate these on the fly, and their processing times are also not too bad, so that you can get results quickly. And last but not least, we also have the interferometric coherence, the interferograms, the phase components, so that you can also do things like PSI when you have your differential interferograms. When running some performance tests, we saw that this is performing nicely. So here we can see just some standard operators running in Snap and in our framework. So for something like multi-looking, this is more or less equivalent on a similar seam. In the calculation of the coherence, we are already about 3 times faster when using the exact resources. Of course, what's the nice thing of our framework, and this is based on Dask, this is also scalable, so we can also put more resources. If we increase the resources, for example, double the resources, then we get even faster calculation here. Because everything is fully parallelized, all of the processing that we have implemented is expressed as Dask processes, and then can scale quite nicely. You can see this here, for example, then when we run this on the full cluster that we have set up for the project, we take 100 square kilometer area and calculate 60 interferograms for 1 year, for example. Then the whole processing is just 160 seconds, which is just 2.5 minutes basically. Or if we do the geocoding of a full stack of coherence pairs, again, just about 60 seconds to calculate these. So that's quite nice. And definitely on the fly doable, so that people don't need to wait too long to get the results. Then here you can see we did some validation then based on other software. For example, our partners in the project, Ares, has also their own in-house software, Presar. So we start carrying out real analysis with the results based on the stacks of data that we have preprocessed here. And by comparing interferograms, we can already see visually that they're very similar, which is great. That's exactly what we want. Even more important, if we do a more complex analysis like PSI here for the city of Bolzano, we can see that the trends in a specific location are actually very much the same and consistent, which is exactly what we hope for. So it means that we have also usable data in our framework. Of course, they're not exactly the same, but close enough that they're useful for real-world applications. Or we did here a comparison of the land cover mapping that we did in the SyncoMap project based on coherence data, where we applied random forest classification over 1 year of shortest baseline coherence of 6 days over the city of Meran in South Tyrol. And also there from the maps, you can already see they're quite similar. There's some issues here with the water class, but that's because we were not able to apply exactly the same training pixels as we did here, because we still had some issues in the conversion to the SAR geometry there. And finally, we did some testing of a backscatter time series for this change detection. We had a big huge storm event here in 2018, where the Vaya storm destroyed many mountain flanks of forest. And here we can see the backscatter time series for two different locations. One, the brownish areas are the ones that have been affected by the storm. Here you can also nicely see how a harmonic series fit to the time series of backscatter. In the non-affected areas remains in the harmonic, whereas in the affected area you get the huge deviation from that, which can then be used to detect these changes on the operational framework scale-offs. So what have we done as a conclusion? We have implemented a prototype implementation for these SLC data cubes. They're fully built and implemented using open source software. The software is also available on GitHub under github.com SAR scripts for the specific part of this project, and all the components to run the Openyo drivers on top of this are under the Openyo GitHub available, github.com/open-eo. And then all of the processing is accessible with the standard Openyo client and our private JavaScript. This is completely based on a scalable processing framework, being the task engine on top of the Open Data Cube. So all the processing is implemented with Xarray and task. It's much more storage efficient than having to pre-process all the data beforehand. If you can do it on the fly, you can test many different parameters and things, and you never need to store the results persistently, since you can just derive it on the fly. And finally, it's also useful in a number of real-world applications using all the different typical SAR and INSAR products, as you have seen beforehand. Still, there's a lot more to do. This project has actually ended now, but we are already looking for some follow-up possibilities, move to a more operational setup. For example, thinking about integrating this into the Openyo platform. We're currently running ISA project where Openyo becomes available as an operational service. There can be done more with respect to the SAR OTF operators, for example, integrating the spectral filtering with different kinds of calibration, putting on top the more higher level operations like the PSI, S-bus, or other kind of typical SAR processors that are needed, and then generate the pre-processing more systematically as an on-demand service. Integrate other SAR sensors. We have seen also in the previous presentation, many more sensors are supported by Snap, so we can of course also generate these base data in different for other missions. And then also look into the metadata generation and card file for INSAR, where I'm curious also about my next speaker and what's coming there, because I think there might be some potential here also to see how they define this. And so definitely a lot of interesting things to come there. With this, I'm closing, and thank you for your attention.
Okay, thank you, Alexander. Now it's the turn of Matthew Gartway, and from Geoscience Australia, with the presentation about INSAR analysis ready data, standard interferometric products to enable further exploitation of Sentinel-1. So please, Matthew, share your screen and start your presentation.
Mario for the introduction. I'm just waiting for the sharing capability. Good evening, everyone. Yeah, I'm calling in from Australia today, where it's winter and night time, so just taking off my big puffy jacket. Chair, if you can see the slides, let me know.
Yes.
Thank you. So yes, today I'd like to talk about INSAR analysis ready data, and the previous speaker gave a good introduction to that with part of his conclusions. This isn't going to be a technical talk. Really, it's an opportunity to raise your awareness of the Seos analysis ready data initiative, I want to talk about encouraging standardization of INSAR products that data providers are producing and disseminating to users. I want to seek the feedback from this expert INSAR community assembled here at the Fringe meeting on standardization for INSAR, and solicit some volunteer effort to join the effort to define the standard INSAR products. So to start off my talk, I'll just show up this very famous paper that was published nearly 30 years ago in Nature. And really, I'm just showing you this again because it's just a reminder that INSAR has been around for a long time. It's a very established technique for measuring and mapping ground surface movements. It's established in the 1990s. So there's nothing, we've been using it for a long time, and we have a very established processing chain where we take SLC products and generate interferometric products from those. And the last speaker gave us a bit of a rundown of that processing workflow. Most of us are doing the same thing where we're downloading SLCs and then we're applying the exact same processing to that data and then doing our independent analysis on top of that. It seems like a lot of duplication to me, and I think we should move forward and start to standardize interferograms and have data providers produce those for us, so that as an individual we don't actually need to produce those products every time. And really, Sentinel One has been an absolute game changer for INSAR, as we all know. It's an operational mission. We get open access to the data, and there's global coverage. So it's been absolutely fantastic for the applications of INSAR. And this has enabled a growing user community to take advantage of INSAR for ground surface movement mapping. We're not just a community of experts anymore. There's a growing community of non-experts as well. And this is enabled by projects like the SNAP project, which we heard about before. They've got tens of thousands of downloads happening all the time with new users coming, trying INSAR, and then there's more and more diverse applications as a result, and bigger and bigger applications. Fringe in Helsinki, we had a session on national ground surface movement products. I think this time we're hearing more about continental products, bigger and bigger scale. Sentinel One's been an absolute game changer in that regard. But I think there's still an opportunity for us as a user community to remove barriers and enable more people to exploit that fantastic and growing archive of Sentinel One data. And that's really why I think we need to sort of set a standard. And I'd like to put forward a question for the discussion session later today. I won't be able to join just because of the time difference, but if I could please ask the chairs to make a note of this question and raise it later for discussion. I'd like to re-ask ESA whether they'll consider distributing higher level INSAR products from Sentinel One. So what I'm talking about is things like interferograms, interferometric coherence, as well as what they already deliver as GRD and SLC products. I think this isn't a new question for ESA, and in the past, it's been somewhat impractical to maybe do those things, but I think it's worth asking that again. But given that I expect that the answer may not change, the onus really is on other organizations to pick up the mantle and start producing things consistently between ourselves so that users get a better experience. And there's a growing list of INSAR data providers. I've got a few examples here. There's the Lixar portal from the Comet Group in the UK, where they're regularly processing the Sentinel One data for the plate boundary deforming zones around the world and making those available on their portal for people to download. And then there's the Alaska Satellite Facility. They now have an on-demand Sentinel One processing service, which they call Vertex. So a user can log in, select Sentinel One data, SLC data for their area of interest, press go, and magically interferogram products are generated and they can be downloaded. And then similarly with the ARIA project in America from JPL Caltech, they have similar processing methodologies. They're starting to make available Sentinel One products. I think we're hearing a bit more about that later in this session as well. And there might even be a lot more data providers than just these three. I know that Geoscience Australia also has plans to make available interferometric products. There may also be startup companies or other industry players that are starting to think about releasing data products. So really, I think it's a good time for us to have this conversation, to define a standard for the InSAR product, because the benefits are fairly obvious. This for the user, there's consistency in the products that they can download. So if I download a product that Geoscience Australia have generated, and then also download a similar product that Comet have generated for the same area, I want to know that those products are going to be consistent. Interoperability, so those products have appropriate metadata defined so that they can be used with products from other data providers. So I'm talking not only about product level data, but also image data, metadata like incidence angle maps and things like that. So these things, I think, are the things we need to define. So with that background, I'll just move on to introducing the Card4L initiative. So this is the Seos Analysis Ready Data for Land initiative, which has been started in the last few years. This is the definition from the Seos website. So Card4L are satellite data that have been processed to a minimum set of requirements and organized into a form that allows immediate analysis with a minimum of additional user effort and interoperability both through time and within other data sets. So, really it's around that message of removing barriers for users, so users can skip ahead in the process to make use of the data products. So at the moment, there are 4 product family specifications formalized through Card4L. There's 2 in the optical space. And then in the SAR space, we've got normalized radar backscatter and polarimetric radar. Both of these the 4 mentioned here are all fairly well advanced, and data providers are already putting their products up against these specifications. In the SAR space, we're now moving towards working on an InSAR product family specification, and we do also have a geocoded SLC product family specification in the works. So if a user comes to the Card4L website, this is what they'll find. They'll see a list of analysis-ready datasets that have been essentially approved to be compliant by Seos. Here's an example of 2 datasets that are approved at the moment. These are optical datasets from Landsat Collection 2. The USGS have generated surface reflectance and surface temperature products and had them firstly self-assessed against the specification and then peer-reviewed against that specification. And there are two things I wanted to notify you of here. There are threshold and target specifications. Essentially, threshold specifications are all the mandatory requirements that a data set must uphold to be considered Card4L compliant. So no surprise there that these 2 data sets are 100% compliant in that regard. And then the target specifications are the nice to haves, the sort of optional things that maybe should be done, but don't necessarily need to be done. And then so for these 2 data sets, we have about 80 to 90% compliance against those. So every data set that's assessed against the Card4L specification is firstly self-assessed by the data provider against the definition, and then a peer review panel does a secondary review on those products. So in the SAR space at the moment, there are 3 products from 3 data providers that are being self-assessed against the normalized radar backscatter specification. Those are from JAXA, the ALOS-2 Global Mosaics, Sentinel One Radiometric Terrain Corrected products from Synergize, and Novasar One Radiometric Terrain Corrected products from the CSIRO in Australia. So as I mentioned, we want to, the purpose of having this talk today is to bring up the concept of InSAR ARD and a Card4L specification for InSAR. No surprise, I don't think that what we're proposing as these products is an unwrapped interferogram, specifically a geocoded unwrapped interferogram as a threshold requirement, and then target requirements of the wrapped interferogram and also interferometric coherence. So we have a draft specification that any one of you could contact me and I'm happy to share that with you. which defines the processing steps for these products and the algorithms that should be used, plus metadata that we believe should be included with the products to enable interoperability. Just to be clear that this isn't designed as a draconian measure to keep everything in line. So it doesn't define everything, and a lot is left up to the data provider. In particular, things like data formats, it doesn't come under the Card4L specification. That's really up to the data provider if they want to distribute geotiffs, netCDFs, or not even distribute data at all, like the SAR-cube example we had before. It doesn't define things like the interferometric network configuration that the data provider chooses. That's really left as a free choice. And also types of processing. So, whether it's operational processing, on-demand processing, campaign processing, or even, SAR-cube kind of processing. So that's really just a really high-level introduction to this topic. I just wanted to raise awareness today. You can find more more information about the initiative at the Seos website there. Any of you who are interested in getting involved or just want more information, please send me an email at this address. I'm really interested to hear from data providers who are already distributing INSAR products or have plans to distribute INSAR products. We'd really like you to get involved with defining the specification. It'd be really good if you could be involved to help influence the direction it goes, so it actually serves your needs as well. So yeah, please get in touch. And I might finally just use this opportunity to plug that we have 2 vacancies in our INSAR team at Geoscience Australia. Applications close on Monday. If anyone's interested in those roles, please send me an email and I can give you more information about those roles. Thank you very much.
Thank you, Matt, for a very interesting presentation. First of all, I would like to recall to the audience, please use the Slido features to post your questions to be discussed at the end of this session. And now I would like to introduce Payush Agram from Descartes Labs that's going to provide the presentation about, well, in line with the last presentations we heard about analysis-ready products derived from Sentinel One data.
Thank you so much. Just a brief word on Descartes Labs. We are a geospatial analytics and data engineering company. We work with large volumes of geospatial data. We ingest all of Landsat, all of Sentinel-2, Sentinel-3, Sentinel-5, and we have been ingesting Sentinel-1 since launch. And we've built out 2 global products, one for radar backscatter and global INSAR coherence that is in line with our other geospatial data sets and available within the same framework. So I want to talk about the development process of this product. As everyone knows, Sentinel-1 comes in 2 flavors. Level 1 products come in 2 flavors, the SLC and the GRD. With the GRD, you can only, you're limited to backscatter analysis, but with SLC product, you can do both INSAR and backscatter analysis. So the basis of all our development work is the SLC product. And an SLC is actually, a TOPS mode SLC consists of a collection of bursts. So it's not a single image. So these bursts form a natural tiling framework for Sentinel-1. Sentinel-1's done a terrific job of keeping the burst synchronized and the pointing control. The footprints repeat very nicely on every pass. The small orbital cube also helps with this, and the orbit quality is also very good. So on the left, I'm showing an image somewhere over Zimbabwe, I think, where 2 different SLCs on 2 different dates. One in orange, one in purple. The spatial extent of the SLC product itself is different, but the bursts within them line up perfectly with each other. So bursts form a very nice styling framework. So we use the bursts as the standard framework. So what we did was we went in and labeled every Sentinel-1 burst globally. I believe from yesterday's announcement that ESA is going to be issuing their burst identifiers for each of these footprints, but we built this we were not sure of the timeline. So we will just add another alias tag that uses ESA's labels as well on these for our work. Initially, when we wrote the abstract for this conference, we were only planning to do IWV transmit, but in the meantime, we've also done all the hedge transmit, and we also started indexing all the EW bursts as well. So we have all those bursts footprints labeled. We plan to complete it by end of this month. We have about 4 months of data left to be indexed, early 2020. As new SLCs come into the system, it compares against the existing footprints. It says it's not there, gets updated. So we see like new acquisitions over Russia happening recently, or over the ocean if they're trying to watch a storm. And following the convention, we label every single SLC burst with polarization with its own unique ID. We're ingesting about 1.5 million bursts per month right now. We index all SLCs that ESA puts out. So labeling is one thing, but to really speed up your data processing, it's the data access that matters. So you need to go beyond just providing a unique ID. What we've done is we've built a optimized data access. We don't need to download the full zip files. We can go handpick the individual bursts out of these zip files. Burst is only 80 megabytes. Which means a single SLC can be processed in parallel. Each burst can be done in parallel. So we've built data mechanism for that based on tools in neuroimaging and genomics community. Why do we do this? Suppose you do INSAR. Most of us don't care about the cross-poll. Why are we downloading 50% of the data and not even touching it? With our data access mechanism, you never even have to touch the cross-poll channel. Also, our swaths are wide. There's a lot of water, data over water. And if you're doing INSAR, we don't need to do anything for those bursts. So again, 29% of the footprints are all water. So if you were to run a global INSAR chain, you only need to download 1/3 of the actual data because you don't need the cross-poll. You don't need the all water bursts. And we also built it in a way where we should be able to switch the source of the data. Could be in our buckets, could be at ASF. If there are other national archives, we could pull the exact 80 megabytes from that as well if they allow us to do byte range downloads. And when labeling the bursts, we also save the metadata. So we have the full metadata for each bursts, so we can look up a stack characteristic without having to touch any of the save files. It's all in our metadata system. And our team has experience with GMT SARICE and SNAP, and we can easily export just the metadata into these formats as well. We can just export a single burst into a SNAP BMT-map format. If people want SICD, we could use SARPy. From our Google buckets, we can pull a single burst in 3 seconds, having nothing on that machine, just our clients. Then if you were pulling this from ASF, it takes about 7 seconds. If you're in AWS US West 2, it takes about 6 seconds, but in general, it takes about 7 seconds to pull a burst from ASF. This fast burst is the key to scalability. And the one caveat is we do need to see the SLC product once, because we need to know the exact byte ranges in the zip files for each burst. That was one aspect of it. That aspect is key to scaling any processing with Sentinel One, PS, MTI, any pipelines. We at Descartes Labs run global change detection models. So there were 2 products that were identified. One was backscatter and coherence, and we wanted to think of ways of really speeding this up. And our platform has optimized tools for automatic tiling with overlaps, all the geospatial data for support for geospatial data. So what we did was we built tools to take single burst in slant range coordinates and geocode it into a 10-meter and 2.5-meter grid. And once you are on a map, you can just leverage all the platform characteristics to do any spatial operations. Backscatter is just absolute value. Interferogram is just cross multiplication, and everything else is just convolution with filters. And this is very similar to the geocoded SLC concept by Howard Zepker, but we do everything with SLCs because we know the SLC data is calibrated. And so we carry the calibrations throughout. So I want to show some examples. So here's our global backscatter product that we built with this. Here's a mosaic of VH sigma naught. The layer we produce is sigma naught E. There's no DEM involved in the backscatter at this point yet. It's posted at 10 meters. We do this for all SSB data. We could do this for SSH, but we don't have any current customer asking for it. So we only do the V transmit data. We convert to dB and save it in 12-bit depth range. This is extensively used in all our change detection and classification. And if you want a stack of a burst, you can just say, give me all the images by this burst ID, and you just get a cube all aligned in geospatial coordinates already. How is this different from other products? We do everything from SLCs. We are slowly in the process of deprecating use of GRDs in our pipelines. It's a lot cheaper. It's computationally more efficient to do everything on bursts rather than get big GRD files. And we are generating an INSAR layer as well. So if you do backscatter with GRD and INSAR with SLCs, we see jitter in the geolocation. Since these come from the same geocoded burst, there's no relative geolocation shifts between these products. What about radiometric terrain correction? That's one difference for our base product. Let's talk about radiometric terrain correction and sensitivity. The orbit tube is 300 meters. The incidence angle change is less than 0.02 degrees. Essentially, our normalization, we're computing the same correction factors again and again for every pass because the imaging geometry is very close to each other. If you were to see if this incidence angle has any change on backscatter at all, you could take any software, Snap, Gamma, and run this experiment. Keep the original SAR metadata, but change the imagery to a constant digital number layer. Then run it through, compute your sigma naughts and your gamma naught t's, and look at ratios. And you'll see that the processing error is in the order of 0.0405 dB when your incidence angles variation is so small. So we believe you can safely use a pixel by pixel static correction factor. So this is essentially what we've done. We've created a global RTC factor product, same at 10 meters, one image per footprint for burst footprint. That correction applies to the entire stack. This is same as essentially creating a co-registered SLC stack and then using the same terrain correction factor for the entire stack, or using the same terrain correction computation. This is well known in the INSAR community, but I see people doing terrain correction on every image, even though it's been acquired from the same geometry. All this was done with Snap 8x for this version. This decoupling of the RTC factor and the backscatter also allows us to just recompute this correction factor with possibly a better method if something comes along without having to reprocess the entire stack. The data layers we provide is this correction factor. We include a shadow layover mask. So one advantage is you can already go over your AOI and see, well, whether my area is going to be in shadow and layover. So because the orbit tube is so tight, this tells you whether your AOI is going to be feasible in analysis in a particular geometry. We also provide local incidence angle. This is mostly for machine learning algorithms that want to take a notion of local terrain into it. We also recommend dilating the shadow layover mask because it's not a perfect mask that comes out of Snap or any other tool. Also, orbit tube varies, so we usually dilate this by 150 meters before we use it. It's an example over LA, and you see in the mountains, the shadow layover mask pixels are shown in white that gets masked out. Those will get imaged from the other pass, and you get to see where you get both geometries or single geometry right from the get-go. The other product we built was the global INSAR product at 20 meters. So we do all VV interferogram pairs less than 24 days. We spatially filtered 20-meter posting using a Gaussian filter, again, searchable by burst ID. Here's an example of coherence of all pairs less than 24 days over Australia in April. We believe coherence at 10-bit depth is more than sufficient. A wrapped phase at 16-bit depth is preserved. But like I said, this is mostly for change detection kind of applications. I will show examples of the erupt phase layer soon too. I also want to point out my colleague Matt Califf's poster, number 594, where we talk about how doing this actually lets us do PS kind of analysis over any AOI in the world, any mine, any dam, any infrastructure facility. Without having any data in hand, in a few minutes, we can geocode the data onto a stack and then do the analysis interactively. So I would highly recommend visiting his poster. Just to show where our product's in action, we use it extensively to track deforestation in say, Sumatra, where it's very cloudy. November 29 to April 2020 image, you can see the deforestation. And with our nice sampling of Sentinel One, we can actually tell from Jan to July where deforestation occurred early. And so this is, so Descartes has a very mature deforestation product that's known for its quality. The other space where this is very useful is in agriculture. This is an area over Central Valley. Again, using the USDS crop data layer, you can see different characteristics for different crops. Almonds, pistachios, alfalfa. Again, the information in coherence is complementary. There are areas where backscatter doesn't change, but you see field activity in the coherence changing in the time series. So this is available globally on our platform anywhere. So what are the next steps with this? The reason I'm hurrying a little is I hope I can use the time to do some quick demos that I have. We will continue indexing a live stream of SLCs. When ESA releases its burst IDs, we'll map it to ours and keep going. We plan to completely reprocess the global INSAR and backscatter product. We've been live since December 2020. We will backfill everything else. We already have numerous country-sized AOIs complete. Our users and customers can use our Sentinel One data access mechanisms and do their own processing. Or if you want our products, we can publish to endpoints for use by you. We've also tested this geocoded burst mechanism, mechanisms with TerraSAR-X and Cosmos SkyMed for certain infrastructure facilities, and it worked really well. So our platform can handle high-res SAR data too. There are other possible avenues to explore. We will possibly look at building a quick look deformation using the global product. And we were thinking about a global ESD offset computation, but there's an extended time annotation that might already cover this. So we would definitely leverage it when it gets released. These are examples of GIFs that we can create with a single line command on our platform. Backscatter, coherence time series, just looking at INSAR phase over Iceland. So let me jump on to the demo. Do I have a couple of minutes? I would only take a couple of minutes to. Minutes, yeah, okay. First demo, here's the live data stream, data that has been actively processed as the SLCs are coming in. This is the SAR backscatter. Each of them is processed burst by burst. It's in a queuing system, so you're seeing we're not the queues picking up individual bursts and processing it. Let me show the INSAR layers. These are the INSAR layers. INSAR coherence, again, it's in the queue and it's being processed burst by burst. And this is the live stream that you're looking at. Ways of searching for bursts. Let me run all cells. For example, here, what I did was I wanted to know what burst footprints hit Paris. And it says these are the unique burst footprints, and that's the way these footprints hit Paris. And you can pick whichever one you want. You say, I want to list all the SLCs that have this footprint ID. And it says it found 290 SLCs, and it lists what the burst number in the TIFF file was and what the IPF was for each of the bursts in this case. Another quick demo, we have a Interferogram Viewer. Since we process all data globally, all this data gets generated automatically. So what you're looking at here is, I'm looking at the southern Shanghai earthquake. USGS issues a unique ID for each earthquake. I just need the ID for the event. I could plug in any other ID. What it did was it looked at our interferogram database, found the shortest temporal space coseismic pair, and it plots the phase and coherence for you. Like I said, our data system already has a lot of tools for mosaicing. It mosaic the individual bursts for me automatically. And if I wanted to download a part of the data locally, say, let me zoom in here and say I want this bit of data. I can say I want track 164.
Hey, Phil, I think we
All right.
are running out of time.
All right. So you get the idea. We have a live backscatter and INSAR product running, and if you want to learn more about it, feel free to contact me afterwards. Thank you.
So thank you, Piyush. Now it's the turn of David Becker, who is presenting California-wide ground displacement mapping using Sentinel One's standardized area INSAR products.
Thank you very much, Mario. So I'm having some WebEx issues, so I'm very grateful that Ryan can present and drive the slideshow. So I'm giving you an update on the work which we're doing with the area team. There's a lot of people behind it. Specifically, we're looking here on some California processing as well, where a lot of the work was done by Simran Sangha and together with Garrett Funning. Next slide, please. So we definitely like the idea from Matt to go for standardization. So a while ago, we adopted actually the NISAR product formatting in terms of a standard displacement product, and we have been generating this. We have been documenting what the formatting is, the different layers, etc., and how it is packaged up. This product is being made available as a NetCDF product, which has multiple groups and layers within it. I recommend if people are interested to go and look at that the website. I looked in the past to some of the CARFRL, and there is quite some agreement already there with the Seos recommendations. Next slide, please. So we have been generating products over regions of interest where a lot of the JPL scientists are working, and then we have been sharing this with the community. So the area product, as I said, is adopting a lot of the NISAR specifications. So it's actually a NISAR beta product. It's being distributed at the ASF DAC. And we have been generating these products over the Sentinel One period and are currently in keep-up mode. We just restarted our keep-up mode and are backfilling some gaps which we had between summer of 2020 and the end of 2020. But as you can see, we have full coverage over California. We have been gradually moving along the US East Coast, and we are processing the Tibetan Plateau as well for some projects from Jill Speltner and Eric Fielding. Next slide, please. So this figure on the top left is already outdated. This was in 2019 when we were running the Getting Ready for NISAR project, where we were testing the throughput to reach NISAR type of volumes. We had about 40,000 products. As of today, we are currently at 130 plus thousand products. Generally, we are our default processing pipeline is to make the nearest 2 interferograms. But for example, over California, we generate the nearest 3 as well as annual pairs to increase the redundancy. On the right-hand side, you can see the product formatting in terms of that NetCDF, where we embed the layers, but also the imaging geometry. And this is kind of different for based on the NISAR specification, where a lot of the incidence angles, the look angles, the baseline, etc., are all provided at 3-dimensional data cubes, which allows to make them very sparse and data compression. So a single Sentinel scene is 90 meters, and a single product is about 70 megabytes. Next slide, please. So how can you access these products? They are being pushed to the ASF DAC. So if you just look under the top left corner, you can see the right box, which is S1 INSAR Beta. Those are the Sentinel, the NISAR Beta products. And you can just use Vertex to go and download them, or use their API tools to go and fetch them. Next slide, please. So the key thing is about these tools, and we might have different product specifications, is usability. So we have developed a package which is called Area Tools, which has a lot of features. It wraps around the ASF DAC API to go and fetch this, and provides additional searching capabilities for filtering. But these tools allow you to pre-process the data sets, merging, cropping, and layer extraction, where we are really leveraging the NetCDF capabilities for virtual data processing. So you could actually you could decide not to download the data from the ASF DAC and extract a single layer using GDAL and only extract the layer which you need. Or you could have downloaded the data and then have performed virtual data processing, where everything is handled through VRT files, which are the virtual files. We are not a time series processing package, but we prepare for time series processing. So we will handle the phase offset between the subsequent frames. We will prepare the coherence, etc., all the information which is needed to go into packages such as MinPy, which is developed by Yunjing, Haresh, and others. So we have been teaching these tools at UNAFCO. There are Jupyter notebooks available, which takes users from start to end through these different workflows. If people are interested, definitely recommend you to look at the UNAFCO webpage for this lecture material, as well as YouTube videos. Next slide, please. So here is an example of one of these time series from those courses. This is made by Haresh, where you can see the central San Andreas near San Francisco. You can also see the Central Valley here with the subsidence signal. And if you want to look at the time series, you can see it's quite a large displacement rate. This is a linear rate. If we now go to, for example, Hawaii, where you have unrest, those would be nonlinear processes. So again, those can be captured very nicely in the time series analysis. This is still a small region analysis. If we later on, I will show you a wide scale analysis over California. The other thing which we have been working on is to make a flavor of the standard product for a co-seismic product. Here we are working to also include dense offsets, to include the ionospheric correction. It will be processed with low latency, and the key trigger, and Piyush pointed already at it, you have these unique IDs from USGS, so you can use that to listen to that feed and automatically trigger your processing from that. So we are building that archive gradually now, and we hope to be opening that up by AGU with all the different correction layers embedded within the product. Next slide, please. So with respect to our California-wide processing, I showed you the tracks before. So here you can see them again. There were 5 descending and 4 ascending tracks, in total 9 tracks. We processed them from 2014 to 2020. We processed them with area tools, and then we went into MinPy to do the time series analysis and get the average line of sight rates. Knowing that some of the processes might be nonlinear, of course, we're looking really at the long-term rates. We also did all the corrections using the GEICOS model, and very much appreciate providing these corrections because we did not use the on-demand system. It was specially generated for us. Next slide, please. So if we now look at the processing, focus first on the top row. This is without atmospheric correction. The markers in the background are the individual GPS stations. We are referencing to a single station at this point, which is not always easy to see, but it's the black marker. So near the black marker, we would be close to the reference point. Of course, if there is some sort of bias, you would see that across the whole network if you would make a scatter plot, which I will show later on. The bottom row shows you after the Geikos correction, and you can see it really helped with removing some of the longer wavelength signals which are still in there. We're still referencing to a single single station in these plots. But you start to appreciate the nice tectonic activities in the area with the central San Andreas, or the fault system in general to appear pretty clearly in both the ascending and the descending data. Now in the far field, you still see quite some displacement signals. You can also see that it starts to deviate from the GPS, so there's still some contamination there. Next slide, please. So now if we would go ahead and do this, the uncertainty analysis as well, you can see that that the reference point is where the driver is of the uncertainty. It's small near the reference point and growing further away. We're currently working on a network approach for tying in the GPS and the INSAR together. But in the long wavelength, again, you can see that the after atmospheric correction, the noise is decreasing. In terms of the scatter plots here we're comparing per track GPS and INSAR. What we observe is that in generally there is agreement when the rates are small, but once the rates become very big, the INSAR is generally underestimating the GPS, and it can be due to aliasing. We're the 90-meter products, so we might be missing signals in the high subsiding regions. So, but overall, you can also sometimes see, for example, let me see which one it is. Yeah, so you just, as long as the slope is 1-to-1, you are good. But if you have a bias with a single station referencing, you would expect kind of a shift. So that would go away once we start correcting based on the network. But overall, the RMS difference is about 7 millimeters per year in worst case scenario. Next slide, please. So now let's look a little bit closer and to the tectonic signals. This is the work that Garrett prepared. Obviously, the San Andreas is a very prominent feature, but you can also see the offsprings around it, the Calaveras, as well as the Hayward Fault in the Bay Area, more up north. But clearly, you can see the discontinuities both in the ascending and descending geometry because they're very sensitive to it. Next slide, please. So if we go and look at some creep profiles, you can clearly see the San Andreas as a big step over, and then you can also see the Pacines Fault, which is the second black triangle, which shows a little step over there. But we have done all these profiles along the whole San Andreas to capture the creep, and Garrett is now proceeding with modeling this. Next slide. We can also see where we have free motion or where we have interseismic creeping and where it gets locked. So the locking really happens near Kalame down south, and up north you can see more of the free interseismic slip. Next slide. So coming to the conclusions, we have this standard product which we have developed, which is publicly available to the community. We are targeting to release a co-seismic archive, which includes all the individual corrections and potentially also the tropospheric correction in there. We have the tools, area tools, to prepare and handle these standardized products, and we are compatible with MinPy package, which has been developed. So in all, we have been providing this training to the community, and definitely I welcome the idea from Matt that there is a standard set of archives out there, and people can just go and use these and perhaps mix these products from one archive to another if there is standardization. And then in terms of the California-wide analysis, we combined about 2,300 standard interferogram products, a whole track of those. And then we did all the atmospheric corrections using Geico's, and the time series analysis applied to it. Generally, we see that after Geico's correction, we reduce the atmospheric variability in the uncertainty, and also the velocity gets cleaned up. In terms of the velocity profiles, we can clearly see the tectonic motion in the San Andreas fault system, as well as the strands besides the San Andreas. And we can see transition to locking near Calame, the city of Calame. I will leave it here, and thank you very much.
Thanks a lot. Thanks a lot. We have some question now to address. I think the first one to Luis about Snap. Do you have plans to change the master-slave wording in the Snap toolbox to something more appropriate, like reference and secondary? This is the question from the audience.
Yeah, so this should be coming in Snap 9. So the only problem here that we haven't done this so far is that we don't want to make a breaking change. So it's baked into the band naming, and so that could affect a lot of people. So we need to be able to do it carefully, that for a time being we can allow both kind of naming and then deprecate the old one.
Thank you. Then we have a very long comment for Matt. Thanks for a great presentation. I fully agree on the importance on broadening the access to INSAR products to non-expert users. Hope to see more engagement by the INSAR community to support the Car4L INSAR product development. I don't know if you have any specific comment on that, just.
Thanks for the comment, and yeah, just really wanted to use the opportunity to raise awareness and have this discussion. So that's all.
I would like to add a question to this, maybe a question for all the speakers, because this this session was mainly about standardization, INSAR ready data, and so on. Do you believe that the future of INSAR will be to have standard measurements available to everybody, or you believe that there will be standardization up to a certain level, but the precise displacement measurements will remain a specialistic job? Maybe I can complement this question with my impression. If we look at the world of GNSS, we see that everyone has a positioning tool in his mobile phone, in the car, and so on. But when we go to precise millimetric, centimetric measurements with the differential GNSS, these remain a specialistic tool. The processing is made by specialized groups, specialized companies, which provide services to the users. So probably we will have the same story here. I don't know, what do you think?
Maybe I can comment on this.
Yeah, sure.
No, I think in general, it's great that we're moving in a direction where the SAR software, the software tools become more available, especially, and make it easier for non-experts to use the data, and then we have more people using it. For many applications, you don't need the last accuracy and everything. Of course, you need to be wary also, because using the not good accuracy in a case where you need it could also propose problems, of course. So there's definitely always a need for experts, but at least it's more available to more people. And I think the GPS comparison is kind of half right, since in GPS, of course, the difference is in what kind of signal you analyze, the code or phase signal and so on. So GPS sensors in the phone, of course, just use the code signal. So that's just a more simple hardware that you have there. That's not actually the case here, because the hardware for us all is the satellite. And from the software perspective, now with cloud computing, we all have the same tools available. So I think in terms of the processing, this can be standardized quite a bit and give the same accuracy available to everyone. Still, the interpretation of the data and so on, of course, needs some experts to be able to do this. But I think in general, we can see with all the tools that we have seen here today, and probably more that are out there, that we don't need anymore to be afraid of using SAR data, let's say, because big part of this is the complex pre-processing chain, and a lot of this can be standardized and optimized and should also be done like this. Of course, they're starting from simple things like the data is organized in complex data in the SLC product, which many Python packages or people are not even know how to open and deal with, basically. And then I think these issues can be overcome. So I think in general, there will be maybe it will be shifting in terms of the need of which experts we need to work with the data, let's say, because more people will have the data available and we can focus more on the analysis part and less on the pre-processing, hopefully, in the future then.
Any other comment?
I can add a thought or a comment. I think, you know, producing interferograms is the standard part, right? And everyone's doing that, and then people are diverging into different applications, and there are different methods for those different applications. So, you know, the question that we tackled in the Seos working group early on was whether we should skip the interferogram as a standard product and move to a time series product, like a displacement product. But we decided that wouldn't be the best choice, because we still have, you know, persistent scatterers versus distributed scatterers, and that seemed a bit more, there was less standardization in that choice at this point. So I think we've got an opportunity now to move further up the chain in terms of a standard, like to an interferometric level. Whether we go all the way to a displacement product, it's worth discussing it, but might still be a bit beyond us.
Any other comment? You know, because there is also the trend of, you know, people, the real user probably don't want a standardized product. They simply want information. So probably that's why I think that maybe they will not, the future probably will not be people playing with the data, even though standardized data, but they simply want information. But I'm not sure. I'm just provoking.
I guess that's definitely true. That's also where, in our way, when we defined the pre-processing, we also finished at the interferograms and the coherence and this level of product. But of course, you can, in other projects, we're looking into more the application side of things and develop full application packets where you get the final result. I guess there's different levels of expertise needed then to get the final application out and the information product. Then and I guess, yeah, for sure, some level of expertise is always required.
I agree with Alexander. I also think that the SAR community in general has a lot to learn in terms of managing data. I agree that the end user wants information, but I think these sort of platforms are needed within our own community to be able to learn to manage large data volumes. I don't think that aspect is very mature. And so, yeah, I think that we need to make progress on that front too.
Okay, I think we can move some of these discussion further this afternoon for who will be participating to the technical session, the technical discussion. We still have to address some targeted questions, like, for instance, Payush, what about handling the phase jumps at the burst edges?
Yeah, so in the live stream, we don't do that. We go purely geometric, just like GMT SAR. But if as a second tag along in a notebook, you could estimate ESD offset and do a phase only correction on top. The ESD stuff doesn't need resampling of the data. You could build that in as a, yeah, I didn't demonstrate. The live stream doesn't do anything about the phase jumps. If you want me to take the other questions as well.
Please.
Okay. The first question was, how do you have the burst at 10-meter spatial resolution? We don't claim that at all. 10-meter posting resolution is whatever the data is. It's just like the GRD product. The GRD product is a 10-meter posting, but its resolution is what the inherent IWSLC resolution is. I didn't get what is the information you need to index the data on. So let's take the Paris example. I said 290 SLCs. If you were to process one burst, you would have to download 290 times 4 gigabytes onto your computer and process the data. What we do is we look at the file once and say that burst is byte X to Y in the zip file. So to process this 290 bursts, we only need 290 times 80 megabytes to move. We don't need the full zip file ever. To know where the burst exactly lies within the zip file and to be able to extract that out, that's why we need to look at the image once. It's clear that one RTF correction value works over the ocean. Does it work over major mountain ranges? Yes. We did test this over lots of stacks. I only showed the ocean to eliminate the DEM aspect of it and say the processing itself has error budget. In the mountain ranges, it goes up to about 0.07 dB, and then you have a long tail. And when you actually use the shadow layover mask on top of it, the long tail is pretty much all shadow layover. So if you are going to not use, you're going to mask those pixels out anyway, you are perfectly fine using a 1 RTF correction value. There was one question for both Matt and me. Accessible, it's a good initiative to make INSAR accessible to non-experts. In my honest opinion, one should provide error maps. I completely agree, but we're at least from our aspect, what we're trying to do is show a really big event or not. We're not trying to do the millimeter scale thing that, like Alexandra mentioned. If there is a big event, at least they should be able to see it. I completely agree about your comment on error bars, especially for subtle deformation or very subtle different signatures. Matt, you may have comments on that.
Interpreted the point a little differently. I thought error maps meant things like, atmospheric correction layers or ionospheric correction layers, and if that was what was meant, then certainly I think in terms of an INSAR specification, we would be thinking about including those specifically as target requirements, but it's all up for discussion in this community. There was one more question for you, Piyush, on how do you tackle phase jumps at burst edges?
Oh, we don't. I think I addressed that. I see another one pop up. The zip files are not optimized for cloud access and subreads. Yes, unfortunately, I don't know if it's possible. It needs specialized tools, and that's what we spent quite a bit of time building. There's tools in other communities, like I said, genomics and neuroimaging, that might help you get started. But then you have to deal with different IPF versions of different characteristics, and there are like 7 or 8 flavors of zip files even within the Sentinel One archive. So you'll have to build tools to handle all of that.
So perhaps following up on that, Piyush, does ISA, like if ISA provides the burst ID, will ISA do the additional step to also provide the byte ranges so we can actually directly read subparts within the in the zip file? Otherwise, the unique burst ID is useful to know, but you would still need to read through the whole zip file to get to a single burst, if I'm not mistaken.
Yeah, so this is really technical. So just the byte range is not sufficient. You need a magic byte sequence to go with the byte range to be able to unzip only part of the zip file. So it becomes a really huge project. I don't know if ISA will plan to do it.
Well, this is Marcus. So this is certainly something that you can recommend or recommend as from the as a community that ISA does something to ease access to parts of the zip archive. So it's something to bring up in the technical session this afternoon at 4 o'clock.
Okay, so Paolo, maybe you want to close the session?
Thank you. Thanks a lot, Mario. Thank you, everybody. Thank you for the very nice presentations to the presenters. Well, again, we would like to recall the poster session this afternoon and the technical session after 4 o'clock, where we are going to also bring some questions that came from the audience and generally to discuss together all these issues brought this morning. So, thanks a lot.
Okay, thanks to everybody. I think it's time for lunch.
Thank you. Bye-bye.